Hello everyone. Today we will learn about ultrasonic echo sound pressure. The echo sound pressure here refers to sound pressure signal received by the probe during the detection process. Teaching objectives of this section are: 1. Learn how to analyze the strengths of defect echoes, establish the conception of comprehensive analysis of problems, and find out the main contradictions. 2. Be familiar with the echo sound pressure laws of several typical defect models. 3. Master the application of echo sound pressure law in practice. Next, please think about what factors will affect the ultrasonic signal reflected from the defect when the beam of ultrasonic waves is incident on the defect. For example, the type of the defect, that is, the nature, the size of the defect, the shape of the defect, the orientation of the defect, and the incident direction of the ultrasonic wave, etc. These factors cause the intensity of the defect echo signal to change. With so many influencing factors, how to measure the defect size as accurately as possible, the current idea is to use the equivalent method. The equivalent method means that under the same detection conditions, if the echo of the defect in the workpiece is exactly the same as the echo of the artificial reflector, the size of the artificial reflector is considered to be the size of the defect in the workpiece. The defect size determined by the equivalent method is called the equivalent size of the defect. In the future study, we will also talk about this style with artificial reflector. We called it a test block. And the artificial reflector is the theoretical method of the actual defect. Commonly used artificial reflectors include flat bottom holes, horizontal holes, spherical holes, etc. Let's learn the echo sound pressure law of these regular artificial reflectors together. Now make the following assumptions. 1. The attenuation of ultrasonic wave in the workpiece is 0. 2. The refraction loss of ultrasonic waves on the regular reflector is 0. 3. The size of the workpiece is large enough that the propagation of ultrasonic waves will not be affected by the side of the workpiece. 4. Take the sound pressure of the echo from the regular reflector to the probe as it echoes sound pressure. First, look at the first type, the echo sound pressure of the flat-bottomed hole. In the test block, there is a circular hole whose bottom surface is flat and parallel to the detection surface. The detection surface in the surface of the test block, where the probe is placed in the figure, and x is the distance between the flat-bottomed hole and the detection surface. According to the previous knowledge, where the distance x is greater than 3 times the length of the near-field region, the sound pressure of the ultrasonic wave transmitted to the bottom surface of the flat-bottomed hole is Px, where P0 is the initial sound pressure, F0 is the area of the wave source, and lambda is the wavelength. According to Huygens' principle, the bottom surface of the flat-bottomed hole can be regarded as the wavelet source of its reflected echo, and the initial sound pressure is Px. The sound pressure when it returns to the probe is the echo sound pressure P phi of the flat-bottomed hole. In this way, it is easy to obtain the echo sound pressure received by the probe on the bottom surface of the flat-bottomed hole is P phi is equal to P0 F0 F phi slash lambda 2 above x above. In the formula, F phi is the area of the flat-bottomed hole, and it is also the area of the reflected ultrasonic wave, which is the law of the echo sound pressure of the flat-bottomed hole. In actual ultrasonic testing, it is equivalent to the reflection area of the defect, which reflects the size of the defect. In this way, in theory, a relationship is established between the size of the defect and the corresponding echo sound pressure. With the help of ultrasonic testing instruments, the echo sound pressure of defects can be displayed in a way that we can understand, so that ultrasonic qualification of defects can be realized. Then let's talk about it. When other conditions remain unchanged, if the diameter of one flat-bottom hole is twice that of the other, it is not difficult to calculate the decibel difference between their echo sound pressures to be 12 decibels. 2. When other conditions remained unchanged, if the distance of one flat-bottom hole is twice that of the other, it is not difficult to calculate that the decibel difference between these echo sound pressures is also 12 decibels. Second, the echo sound pressure of the long horizontal hole, as the picture shows, when the distance x is greater than 3 times the length of the near field area, the echo sound pressure is P phi is equal to P0 F0 slash lambda x, and then multiplied by the square root of the phi slash 8x. When other conditions remain unchanged, the distance between the two long horizontal holes is twice as long, and it is not difficult to calculate that the decibel difference between their echo sound pressures is 9 decibels. If the diameters of the two long and horizontal holes differ by 1 time, the decibel difference between their echo sound pressures is 3 decibels. 3. The echo sound pressure of the short shear hole. When the distance x is greater than 3 times the length of the near field area, the echo sound pressure is P phi is equal to P0 F0 slash lambda x multiplied by L slash 2x and phi slash lambda under the root sign. In the formula, L is the length of the short horizontal hole. When other conditions remained unchanged, the distance between the two short shear holes is doubled, and the decibel difference between their echo sound pressures is 12 decibels. If the diameter of the two short shear holes differ by 1 time, the difference in decibels between their echo sound pressures is 3 decibels. If the lengths of the two short shear holes differ by 2 times, the decibel difference between their echo sound pressures is 6 decibels. Fourth, the echo sound pressure of the spherical hole as the picture shows. When the distance x is greater than 3 times the length of the near-field area, the echo sound pressure is P phi is equal to P0 F0 slash lambda x multiplied by phi slash 4x. When other conditions remained unchanged, the distance between the two spherical holes is doubled, and the decibel difference between their echo sound pressures is 12 decibels. If the diameters of the two spherical holes differ by 1 time, the decibel difference between their echo sound pressures is 6 decibels. 5. Echo sound pressure of a large flat bottom and curved bottom surface of a solid cylinder, as the picture shows. When the distance x is greater than 3 times the length of the near-field area, the echo sound pressure is Pb is equal to P0 F0 slash 2 lambda x. When other conditions remain unchanged, when their distance are doubled, the decibel difference between the echo sound pressure is 6 decibels. 6. The echo sound pressure of the curved bottom surface of the hollow cylinder, as the picture shows. When the distance x is greater than 3 times the length of the near-field area, the echo sound pressure is Pb is equal to P0 F0 slash 2 lambda x multiplied by the positive and negative 1 slash 2 power of d slash d. In the formula, d is the diameter of the inner hole, and the capital D is the outer diameter. When the probe is placed on the inner wall, the positive and negative sign in the formula take the negative sign. Otherwise, take a positive sign. The echo sound pressure formula of the regular reflector just described does not consider the attenuation of the medium to the ultrasonic wave. Otherwise, the end of each formula should be multiplied by the decay factor. Below, we take the echo sound pressure formula of the flat-bottomed hole as an example to illustrate its application. Detect a forging with a 2.5 P20Z probe on a large flat-bottomed test block with a thickness of 100 mm. The bottom wave height B is equal to 50 dB. Known CL is equal to 5,900 m/s. Alpha is equal to 0.01 dB/mm in the forging. Alpha is equal to 0.005 dB/mm in the test block. The difference between the surface coupling loss of the two is 6 dB, and a defect is found at 150 mm during flat detection, and its wave height is 15 dB, find the equivalent size of this defect. The continent of the subject is known that the probe model is 2.5P20Z, indicating that the ultrasonic frequency is 2.5 MHz and the diameter of the wave source is 20 mm. The idea of solving the problem is that, according to the question, it is known that the bottom wave height HB is the test block is equal to 50 decibels, and the defect echo height HF in the workpiece is equal to 15 decibels, and the equation 20IG open parenthesis capital HB slash capital HF close parenthesis is equal to 50 minus 15 is equal to 35 decibels can be listed. It should be noted that the reasons for the 35 dB height difference are three aspects: defects and large flat bottom reflection differences, material attenuation differences, and surface coupling differences. Therefore, the surface coupling differences should be deducted when using the flat bottom hole sound pressure formula described earlier. Just think, if there is no surface coupling differences, should the height difference between the two echoes be 50 minus 15 minus 8? Obviously. After this analysis, we can solve it as follows. First, finding that the wavelength is equal to 2.36 mm and the length of the near field area n is equal to 42.3 mm, and then we can judge whether the distance is greater than 3 times the length of the near field area. This is the precondition for the next application of the echo sound pressure formula of the flat bottom hole. It is judged that it is greater than 3 times the length of the near field region. Therefore, the echo sound pressure formula of the flat bottom hole can be listed for calculation. Finally, the equivalent flat bottom hole size of the defect is 4.36 mm. It should be noted that the size of the equivalent flat bottom hole must be emphasized in the end. That is, we use equivalent method to detect, and the result can only be the equivalent size, not necessarily the actual size of the defect, and they are different. Through the explanation of the example just now, we have a preliminary understanding of a method of ultrasonic detection of quantitative defects. With further study in the future, we will learn other methods of quantitative defects and other applications of the echo sound pressure formula. That's all for today. Thanks for your watching.